Now on BBC One, Patrick Moore presents The Sky at Night.
Good evening. In this programme, we're going to talk about Machos and Wimps and dark matter and things in deep space. But first of all, a few news notes. In August, the International Astronomical Union, the controlling body of world astronomy, met in England for the first time in 30 years, and all branches were discussed. For example, Earth-grazing asteroids. And in fact, on September the 1st, one of these tiny bodies brushed by it only 2.5 million miles, and that's not very far, even though I'm glad to say this one was in no danger of hitting us. We also talked about the death of a comet, Comet Linear, which had been quite bright. There's a Hubble view, and as it neared the sun, it broke up. And here's the comet in the process of disintegration. Quite a different theme. Over in northern Chile, the YEPAM, the fourth 8-meter mirror of the VLT, or Very Large Telescope, is now in full action. And here the first picture ever sent back by YEPAM, part of the Milky Way, and there a planetary nebula. And now that all four 8-meter mirrors are working, the VLT is much the most powerful telescope ever built. And now on to our main theme. Look into the night sky, the clear night, you see stars, nebulae, and galaxies. In our galaxy alone, 100,000 million stars, all pouring their energy into space. And yet, you know, there's now very good evidence there's plenty of matter up there that we can't see. Material we can't see at all. In fact, we may be seeing only a tiny fraction of the total universe. And to discuss this fascinating dark matter problem, welcome back to one of our regular guests, Iain Nicolson. Welcome back, Iain.
Thank you.
First of all, how are we sure that dark matter really does exist?
Well, I think the first key strand of evidence is to look at the way in which spiral galaxies rotate. Our own galaxy, the Milky Way system, of which the Sun is a part, is a spiral galaxy. If we look at it edge on, we see a flattened disk of stars and then a great bulge, a concentration of stars in the middle, and our Sun itself is about 25,000 light years out from the center towards the edge. If we tilt the galaxy over and look at it face on, then again we see the position of the Sun, and we see that the disk of the galaxy has got a well-defined spiral structure. The bright stars and gas clouds are organized in a spiral pattern. And many other galaxies are quite similar in appearance. Here's another one, a particularly fine spiral galaxy called M83, and this beautiful photograph is by David Malin. You can see there the winding spiral arms very clearly. Now, in that galaxy and in our own, the greatest concentration of stars is towards the center. That's where most of the light is in these images. And if it were true that most of the mass is concentrated where most of the light is, then if we look at the way in which galaxies rotate, we would expect that the stars and gas clouds towards the outer regions of a galaxy would be revolving around the center more slowly than the ones closer in, just like the way in which the planets further from the Sun go more slowly than the innermost ones.
Kepler's laws.
Kepler's laws, indeed. Now, what we can do is actually try and measure this. And if we do that, let's look at a graph. In the vertical direction, we're measuring the speed of rotation. In the horizontal direction, distance from the center of the galaxy. And if most of the mass were near the center, then we would expect the rotational velocity to rise until you got to the edge of the bulge, and thereafter it would begin to drop off in accordance with Kepler's laws. The speeds would decline. But in fact, when we look at our galaxy and other galaxies, we find that the stars and gas clouds towards the outer edge are moving just as fast, if not faster, than the ones closer in. So the curve stays flat or even rises rather than dropping down as we'd have expected.
In fact, there must be dark matter there. Otherwise, the galaxies wouldn't rotate in the way they actually do.
That's exactly right. In order to make the stars and gas clouds in the outer regions move as fast as they do, there has to be a much greater gravitational attraction acting on them. And that gravitational attraction has to be provided by a huge halo of dark matter surrounding the visible part of our galaxy. And that dark matter is dark in the sense it gives out no light. It gives out no kind of radiation like X-rays or radio waves that we can detect, but it's in there to have the gravitational influence that we see. Now, this is the case for galaxies like our own. Another key strand of evidence is to look at clusters of galaxies. Most galaxies are organized together in groups or clusters. This happens to be the Virgo cluster, some 50 million light years away. And the individual member galaxies all roam around at their separate speeds in random directions inside the clusters to which they belong. And the speeds at which they're moving are such that if those clusters didn't have a great deal more mass than we can see, there wouldn't be enough gravitational attraction to hang on to their members. The member galaxies would have escaped and the galaxies would have dispersed long ago. And generally speaking, the bigger the structure you look at, the more dark matter you need to have to hold it together. So we can't directly see the stuff, but it's really got to be there in order to explain the way that galaxies move.
Kind of cosmic glue, in fact. I wonder, Iain, now, what can this dark matter be?
Well, one possibility, perhaps a rather mundane possibility, is that it's mostly made up of very dim stars or star-like objects which are so faint that they don't give out enough radiation for our present techniques to register. Possible candidates might be white dwarfs or black holes or brown dwarfs. Now, brown dwarfs are, in a sense, failed stars. They have masses of less than 8% of the mass of the Sun, and because of that, they never get hot enough in their centers for the same kind of nuclear reactions to get going there as power the normal stars. Here's an example of a brown dwarf. It's a photograph taken very recently by the VLT of an object called TWA5b, yes, which is the very faint star just above center in the picture above its very bright companion. So that's a very subluminous star. It's a brown dwarf. Now, we're beginning to get evidence that there's really quite a lot of brown dwarfs out there. Here's a couple of images taken by the Hubble Space Telescope. The one on the left's an ordinary visible light view of the Orion Nebula, a glowing cloud of gas. And on the right we see an infrared image of the same area of sky, which penetrates through dust and allows us to see deeper into the image and pick up a lot of faint objects there. A lot of these dim, faint points of light, reddish points of light, are brown dwarfs. There's probably about 50 there mixed in amongst the brighter ordinary stars. And another more recent image taken by the UK infrared telescope of the same area of sky shows even more. There's probably about 100 brown dwarfs mixed in amongst the ordinary stars there. And interestingly, it looks as if some of them have got masses that are only around about 10 times the mass of the planet Jupiter, as if they were sort of freely floating planets, roaming around, gas giant planets, not attached to any particular star. So there's certainly evidence of a lot of brown dwarfs there, but when you look at how low their masses are, even when you add them all up, there's nothing like enough matter to account for the missing mass needed in the dark matter halo.
So brown dwarfs can't solve our problem. We must start looking further afield.
Well, another possibility is that things like very dim white dwarfs, black holes, planetary mass objects in the halo of our galaxy have collectively come to be known as Machos. Massive astrophysical compact halo objects. And people have been looking for them by looking for a phenomenon called gravitational microlensing. Albert Einstein, when he developed his general theory of relativity, showed that the presence of a large mass of material bends space and causes rays of light to move in curved paths. Now, if we imagine that we're looking at a distant star and we've got a ray of light coming from that star cross into our telescope, producing the image that you see on the right-hand side there, if a massive dark object, a macho, interposed itself between us and that star, it would bend rays of light, bring them to a focus into our telescope, gather more light and make the star appear temporarily brighter than usual. Then when the macho moved away, the star would revert to its original brightness. So this is really quite a distinctive kind of phenomenon. If we plot the light curve, look at the way that the light varies during the event, it rises quite sharply, it drops back down in a symmetrical way, and not only that, but because gravity affects all wavelengths of light equally, then no matter what wavelength you look at, whether you're looking in blue light or red light or anything else, you'll see exactly the same rise and fall in the same sort of way. And that's the kind of signature that people are looking for.
Well, have any matches been definitely found so far?
Well, a number of groups have been looking, and in particular there's a group, an American and Australian joint project called Macho, that over the last 6 years has been looking at something or monitoring something like 20 million stars. Part of the problem is that to get an event, the alignment's got to be so good that you've really got to be looking at millions of stars over long periods of time to have any chance of seeing any at all. And what the Macho team have done is to look in the direction of the Large Magellanic Cloud, a nearby neighbour galaxy about 170,000 light years away. And that, of course, contains lots of stars. And if there are any Machos in the foreground, in the halo of our own galaxy, and they pass in front of certain stars, then you might get microlensing events. And by the beginning of this year, they reckon that they'd seen about 13 to 17 events that could well be microlensing in our galactic halo. Here's one particular example. In this image here, you can see a rather faint star in the center of the screen, picked out by the yellow circle. That picture was taken in January 1996. If we look again in November 1996, you can see how it's brightened up. And that's a very characteristic brightening of the sort that you'd expect with microlensing. Looking at the time that this event took to take place, it looks as if the massive object responsible was about 6 times as massive as the Sun and was probably a black hole in the outer fringes of our own galaxy. But when we look at the average duration of microlensing events, admittedly from a fairly small sample, it looks as though the average mass comes out to be about 60% of the mass of the Sun, which is much more akin to the masses of white dwarfs than to brown dwarfs. But whatever they are, again, a very small sample, but it looks as though when you add them all up, there won't be more than enough material in the form of Machos to make up more than 10 or 20% of the mass needed for the galactic halo.
So, alas, Machos fail us also. Well, what about other possibilities?
Well, Machos, of course, are examples of baryonic dark matter. That's to say, matter of the sort that makes up ourselves. Baryonic matter consists basically of protons and neutrons, the building blocks of atomic nuclei, and therefore the building blocks of stars and planets and galaxies and people. But cosmologists have been thinking for a little while now that to account for the amount of dark matter that we need to account for, perhaps most of it has to be in the form of non-baryonic particles, particles which hardly ever interact with ordinary matter except through the agency of their gravitational fields. Now, the first candidate that was suggested was the neutrino. We know that neutrinos exist, but as originally postulated, they were rather bizarre particles. They would have 0 electrical charge and 0 mass. So if you had a stationary neutrino, it would weigh nothing at all. But in recent times, theoretical work and some experimental work seems to suggest that neutrinos do, after all, have very tiny masses. Now, according to the Big Bang theory, there should be very large numbers of neutrinos about 100 million of them in every cubic meter of space. So if they had a mass greater than about a 10,000th of the mass of an electron, then there would certainly be enough of them, in principle, to account for the dark matter halo of our galaxy. But in recent times, there have been experiments that have been trying to measure the mass of neutrinos. In particular, there have been some results from the Japanese detector called Super Kamiokande, and they seem to support the notion of neutrino mass. Here's the detector. It's a wonderful thing.
Amazing thing.
It's about a 40-meter drum, basically, filled with 50,000 tons of ultra-pure water and surrounded by about 13,000 photomultiplier tubes, which you see as the little white blobs here. And to get some idea of the scale of this thing, you can just see 3 technicians floating around in an inflatable dinghy there inside the detector. And of course the detector has to be buried deep underground, under a kilometre of rock or so, to protect it from other particles like cosmic rays that would produce spurious results. Now, the Super Kamiokande results don't directly give us the mass of a neutrino, but they do suggest that it's finite and probably less than about a millionth of the mass of an electron.
Not a lot.
Not a lot indeed, and if it's as low as that, then despite the fact there's a lot of them around, there wouldn't be enough mass contained in them to account entirely for the dark matter halo of our galaxy.
Well, Ian, now next, what about Wimps?
Well, Wimps, it's a lovely name, isn't it?
Lovely name.
It's an abbreviation for weakly interacting massive particles. And these are particles which in some ways are rather like neutrinos. If they exist, and they're entirely hypothetical at the moment, they don't have electrical charge, they hardly ever interact with ordinary matter, but the key difference is that they are very massive, 10, 1,000 times as massive as a proton. So they'll pack quite a punch. And if, for example, we're sitting here, there's probably a huge number of Wimps around, maybe billion of them passing through your body every second, but you don't notice it. But on the very rare occasion that a WIMP collides with an atomic nucleus, traveling, say, at about 1 million kilometers an hour, it's going to hit that nucleus and cause it to recoil, rather like a pair of snooker balls colliding and rebounding off each other. So people are looking for that kind of event.
Have any collisions been found yet?
Well, a number of groups have been looking for them. There's 3 different key ways in which you might be able to register the impact of a WIMP on your detector. One is to measure the tiny quantity of heat, the microscopic amount of heat that's deposited. A second approach is to look for the electric charge that's released when the WIMP ionizes and throws charged particles off the atomic nucleus. And the third approach is to look for the light that's emitted when the nucleus itself, the one that's been hit, recoils through the surrounding water. So people have been looking for those kinds of things. Now, one particular group, an Italian group called the DAMA project, announced some results at the beginning of this year that suggest that perhaps, and only perhaps, they may have detected WIMPs in their particular detector. And the line of argument is as follows. If, indeed, we have a great halo of WIMPs surrounding our galaxy, then the Sun, which orbits around the center of the galaxy at a speed of about 220 kilometers a second, will be plowing through these WIMPs all the time. So it will be as if there's a sort of wind, a flow of WIMPs flowing past the Sun. Now, of course, the Earth goes around the Sun at about 30 kilometers a second, and for half of the year it's going in roughly the same direction as the Sun, and the other half of the year going in the opposite direction. When it's going in the same direction as the Sun, around about June each year, then its speed through the WIMP wind will be higher, and we'd expect to detect more events. When it's going in the opposite direction to the Sun, in December, then our speed through the WIMP wind will be lower, and we should see fewer events. And that's what the DAMA results appear to indicate. As you can see here are the measurements over the past 4 years. You can put a sort of a sine curve through them and pick up what looks like a periodicity reaching a maximum every June or so. And that's what you would expect if the solar system were plowing through a background of WIMPs. But I have to emphasize this is a very small scale effect. That rise and fall is only about 1% on top of lots of other detections, most of which aren't WIMPs at all. So one could say there's WIMPs there, but it's not definitive. And the American group, the CDMS, the Cryogenic Dark Matter Search, has also been looking for WIMPs. It's picked up about 13 events by the beginning of this year, but they reckon that each of these events is in fact a stray neutron from natural radioactivity and not really a WIMP at all. They also argue that if the DAMA results were correct, then the CDMS team should be seeing far more results than they actually do. So the jury's still very much out on whether WIMPs have mass and have been detected.
I wonder, do you think in the near future we really will solve the dark matter problem?
Well, we're certainly not there yet. Certainly there's something out there that's providing the gravitational influence to make galaxies behave as they do, but whether it's ordinary matter in the form of Machos, neutrinos, WIMPs, a combination of all 3, or indeed something else, we can't really say at this time.
Well, Iain, it's a fascinating problem, and we'll come back next month and take it further and look at dark matter in the far depths of the universe, how it affects us, how it affects the universe, and how it affects ultimately our own fate. Iain, thank you very much.
Thank you.
Don't forget our website, www.bbc.co.uk/Sky at Night, or of course CFAX page 620. And next month we'll return and go on with this fascinating dark matter problem in the far reaches of our universe. Until then, good night.